So looking at the handout I gave you, it is this graph, y equals x squared plus 2, that handout, that yellow sheet shows you. And this is the actual graph with the area underneath the graph until the x-axis highlighted. And what you have on your sheet is a picture of what's called a lower sum. Okay, so what we have here is a bunch of rectangles that, if I add up all the area of all the rectangles, it will be less than the area of the shaded portion above, right? If we just take a look at that shaded portion above, look at them both together. This area is more than the rectangle's area, right? And that's what a lower sum is. It's an underestimate of the area underneath the curve using rectangles to estimate it. What we do is we cordon off equal widths for the rectangles, and then we go up to the lower point. So this rectangle, that's the height, this rectangle, that's the height, and that's the height, and that's the height. And each of the points where the height is rests on the curve itself. So the function y equals x squared plus 2, if I evaluate x squared at 2 at 0.8, that represents the height of this rectangle. So we have the ability to establish, based on the formula, what the height of each of those rectangles is. So we can find the area of each of those rectangles individually, add them all up, and that gets us an underestimate of the area, which is kind of close but not exactly, because we're missing it by this much, all these little spaces here. All right? If, instead of drawing the rectangles on the low side, if I were to pick the high side, go across this way, that's called an upper sum. So if I'm at the high side, go across this way, you can see each of these rectangles also estimates the area under the curve, but it's too much. If you look at them side by side here, maybe, that's the button I want to press, there we go. This is about the same as that, and this is about the same as that. They're not exactly the same, they're pretty close, right? So if I take this overestimate and that underestimate, add them together and divide by 2, it's going to be pretty close to the actual area under the curve. That's the lower and upper sum method. All right? The technique we're going to use to do this, it's all going to be done in tables with numbers. But the technique I'm going to give you is going to allow you to find the height of each of these rectangles. All right? And the width is going to be whatever you decide to be. So in this case, I broke up a width of 2, right? 0 to 2 is 2 spaces, into 10 rectangles. 2 divided by 10 is 0.2, so each one's 0.2 wide. So that's delta x. That's what that's called. All right? Delta x is simply how wide the interval is. Divided by the number of rectangles we choose to use. So it's not always going to be 0.2. If I were to use 20 rectangles on this, 2 divided by 20 would be 0.1. Every one of those rectangles being 0.1 wide. The more rectangles you use, the more close your estimate's going to be to the right answer. But also the more numbers you're going to have to work with. So there's some sort of happy medium with these. The right number of rectangles that get you a correct enough answer where you don't get writer's cramp writing down all the stuff. All right? And what we're going to use to do this is this technique here, and the calculator is going to be doing a lot of the work for us. It's going to be evaluating things for us. It's going to be our job to record on paper what the calculator tells us. All right? So you determine the width of the approximating rectangles, delta x. Again, it's the interval length divided by how many rectangles. I want you to make an x, y, delta x area chart, and that looks like this. X, y, delta x area. Notice the delta x is just one big row here because it's the same for all of them. You can put 0.2, 0.2, 0.2, 0.2 if you feel like it. Just know that 0.2 is this for every one of them, right? Right. Full screen here so it's bigger. There we go. Enter the function, whatever it is you're trying to find the area of. So the area under the curve, that's y1. Enter delta x as y2. So if delta x is 0.2, y2 equals 0.2. If delta x is 1, y2 equals 1. Delta x is 0.7, y2 equals 0.7. So whatever number delta x is, that's what y2 should be. And you'll put y1 times y2 as y3. So here it looks like this. go y equals, clear, clear. So in the case of this one, I'd put x squared plus 2 as y1. Don't do this because we're going to do an actual example problem in a minute. But y1 is x squared plus 2, the function. We're doing delta x was 0.2, right? And then I want to do y1 times y2 is y3. So I go to variables, y variables, function y1 times variables, y variables, function y2, just like that. All right? And what I always do is I turn off y2. You don't have to do that, but by turning it off, you're not going to see a whole bunch of 0.2s in a row.
So confusing.
Yeah, it won't even confuse you, it'll just be in the way. All right, so you just turn off y2. So when I go to the table, all I see is y1 and y3. y1 the function, y3 the area. All right? Because what's happening here with y3 is it evaluates the function at whatever x is. That's the height of the rectangle. y2 is the width of the rectangle, so y1 times y2 is the area of the rectangle. All right? And for each different x, it's going to find the area of each different rectangle. Then it says go to table set. Right above window, there's table set. We usually have it on ask, almost always, right? With these, I just want to get, I can type it individually, 0, 0.2, 0.4, 0.6. My finger starts getting sore. All right. If I start at 0, the starting point of this graph, and to put a delta table, which is delta x at 0.2, and turn the independent on to auto, if I go to my table, then it immediately already has all those numbers on there. y1 is the height of each of those rectangles, y3 is the area of each of those rectangles, and just like that we have all the data we need in order to find the area under this curve. That's how this works, all right? And then if you add all but the smallest one, so smallest one's 0.4, add up all those, that's the upper sum. If you add all but the biggest one, that'd be all those, that'd be the lower sum. Add those together, divide by 2, you get your area. And it's approximately right. Okay, pretty close. The answer is 6.75, you might get 6.72. It's really, really close. All right, so let's do this one. Estimate the area under the curve y equals 6 over x from x equals 1 to x equals 6 using 10 approximating rectangles. So that's how these problems typically look. And it does tell you to compute using upper and lower sum. The book, they say using upper endpoints, lower right endpoints, left endpoints, that kind of stuff. Today I want everything to be lower and upper sums, no matter what the book tells you. What I want you to get from the problems in the book is going to be what's the function, what's the interval, and how many rectangles we're going to use. Okay, use the upper and lower sum technique for the problems tonight. All right? So, if I'm doing this problem, job 1 is to establish what delta x is. So delta x is going to equal the interval length, which is what? Say again? 5, very good. From 1 to 6 is 5, right? If you just take the big number minus the small number, that's what the interval length is. Divided by the number of rectangles, which is 10, that gives me a delta x value of 0.5. If it happens to come out as a fraction that doesn't work well, like let's say 1/7 or something weird like that, I don't ever make you do 7 rectangles, but let's just say it did. 1/7 is y2. Just type it in just like that. Don't round that number. You'll get much more accuracy by using the fractional formula. But if it comes out as a nice terminating decimal, by all means use it. If it comes out as 2/3, put y2 equals 2/3. That's better than 0.67. Or even better than 0.666667. Like even if you went a lot of decimal places, 2/3 is infinity decimal places. That's better. All right. So once we've established delta x, we're going to our calculator. I'm going to go to y equals. I'm going to clear this out. I'm going to leave that the same. So if you do a bunch of these problems, y1 times y2, that's what that one's going to be every time. y1 is the function, which was 6 divided by x. y2 is delta x, which is 0.5. And again, I'm going to turn that off. If you don't turn it off, here's what happens. It just puts a whole line of 0.5s there.
How do you turn it off?
Okay, so the way you turn it off is you go, just go on top of the equal sign like that. So it's blinking on the equal sign. Hit enter, and the equal sign turns off. So you should see how these are both highlighted, but that one isn't. So again, if you get on top of the equal sign, hit enter, it turns it back on. Get on top of the equal sign, hit enter, it turns it back off. But again, if it's on, all you're going to do is get a whole row of 0.5s, which it's not terrible to have it there, it's just not necessary to look at it. Okay? Now, as far as setting the table is concerned, again, you're going to do a table set on every one of these problems. Table set is where do you start and how much do you go up by. That's what it's looking for. That's the table set every time. So if I go to my second window, I want to start at the number 1, and I want to go up by 0.5 at a time. And again, I've got it set to automatic. Okay, so what that does for me is it automatically starts at 1, goes up 0.5 at a time, and gets me this nice data.
Will it always be on automatic until you switch it?
If you switch it back to ask, that's when it'll be back on ask.
Okay.
Until you switch it back, it'll be automatic.
Okay.
So keep that in mind. If I try to delete this, it won't delete because it's automatically set to start there. And if I needed to go further, so let's say I need to know what 6.5 was. If you just push down, it'll keep going. All right. Or if, and I don't know if it goes back up. Let me see. Yeah, it does go back up. Good. The old calculator didn't. It would just pop up to X and then you'd be frustrated. But yeah, so that's what happens here. So it starts at 1, goes up by 0.5 at a time. Yes, Renee?
I'm sorry. I don't know how you make the y1 times the y2.
Okay, so again, to get the y1 times y2, you're down here, hit the variables button. Then you have choices of variables, y variables, and color. You want to choose y variables, so just press over to the right and it moves over there, gives you this whole list. That takes you to the functions or whatever we want functions, hit enter, and then you have your whole list of y's. And then you pick the one you need, and then go from there. No problem. All right, so I got my chart here, and now I'm going to fill it out. So again, next job is to actually record your data, so I'm going to do that. Kind of nice if that fit better. Let's see. Shrink that a little bit. There we go. Perfect. So what I would do here is I would write down 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, and 6. And then y1 is the height of every one of the rectangles, and that will be the second column here, which is 6, 4, 3, 2.4, 2, 1.7143. I want 6 decimal places, typically rounded, so 7142857. 1.5, 1.33333. I'm going to guess that just keeps going. And then 1.2, 1.0909, probably 09, and then 1. To get those extended decimals, you can just see at the bottom if you're highlighting the numbers 1.5, all 3s, that's good. 09 repeating, that's good. So you can just highlight the one you're looking at and you see the bottom screen how many decimal places you need. You get like 6 decimal places on these. That should be a 6 there. Alright, so delta x was 0.5, and then area is just this column, and again we got a few decimals here that go beyond. So 3, 2, 1.5, 1.2, 1.857143, 0.75, 0.6 repeating, 0.6, 0.54, 5454, 5. So that will round up, and then 0.5. And just like that, we got the area of each of those rectangles. And notice 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 areas we get. And we're trying to do how many rectangles? 10. Okay? So when you do upper and lower sums, you're going to have one more rectangle area than you have actual rectangles. And the next part tells you that the upper sum is the area of the 10 biggest rectangles. So this blue part here represents the upper sum. And to find the upper sum, I simply add those numbers together. Easiest way to add those numbers together? calculator, so I'm going to do that. So I'm going to do 3 plus 2 plus 1.5 plus 1.2 plus 1 plus 0.857143 plus 0.75 plus 0.666667 plus 0.6 plus 0.5454555. You gotta move 545 and the 5 rounds the last 4 up to a 5, right? If I hit enter, that's my upper sum, 12.119625. So upper sum equals 12.119265. Now the lower sum is much easier to evaluate. The lower sum is the sum of these smallest 10 rectangles.
You put 5, 6, and 6, 5.
Thank you. Messing up on those two would be worse than messing up on the first. Not would be less than messing up. I've made that 21 instead of 12. That'd be a much bigger mistake. Thank you for fixing me. All right. The lower sum, notice it's the exact same 10 except for this is missing and this is added, right? So you just typed in all 10 of these numbers, right? Here's how you get the next sum, the lower sum. Just do plus 0.5. It does the previous answer plus 0.5. Subtract 3. Add the smallest, subtract the biggest, and that's going to be the other 10, right? Make sense? If I added up these 10, if I take that one away, now I got these 9 and add that one, right? So the previous answer, add the smallest, subtract the biggest, that'll be the lower sum. 9.619. 265. All right. So upper sum too big, lower sum too small. Correct answer somewhere in between those two numbers. And again, the average of those two numbers will be very, very close to the right answers. That's what we're looking for the approximate area is the average of those two answers. So if I just take parentheses 12.119265 plus 9.619265 in parentheses, take that entire sum in parentheses and then divide by 2, it comes out to 10.869265. And that's square units. That's the entire technique done correctly.